Hello everyone, and in this video we're going to begin limits in maybe pre-calculus, or maybe you're starting this in calculus. Either way, we're going to look at limits and their notation. So first I have a question here. If f of x equals x squared, then what is f of 3? So remember from just algebra, you will plug in x equals 3 into the function here. So you'll say f of 3 equals 3 squared, and 3 squared is just 9. Now, in the next question, we're asked, what is the limit as x goes to 3 of f of x? So I think a good way to explain this is, let's look at a graphical representation. So when you're looking at limits, you don't look at the exact value of the function at that point. So technically you're not plugging in x equals 3 right away. You're getting really, really, really close to that point. So let me just draw maybe a random function here, and then let's say this is x equals 3. So you're looking at this point right here, and you're trying to get really, really close to this point, but never actually hit it, okay? So I can kind of approach that from the left and the right side. So limits are all about, you're not equaling that value, you're just getting really, really, really close to it. So I could plug in, for example, f of 2.99 or something like f of 3.01. You're getting really close to that value, but you're not equaling it. I just want to emphasize that about what limits are. You're not equaling that point. You're not at the point. You're just really, really close to it. So how do we evaluate limits? Well, I'll have a separate video of how you can evaluate different kinds of limits. But for this video, we're going to look at what's called direct substitution. Sometimes you can plug in the value it's asking for into the function right away. So it's saying, what is the limit as x goes to 3 of f of x? That's how you would read that, by the way. The limit as x goes to 3 of f of x. So what you can do is you can plug 3 in. You can plug 3 into that function. So 3 squared equals 9. So, and that's how you would evaluate this particular limit. Now, something we're going to explore later is something called continuity. Maybe you touched up on this in pre-calculus, but we're going to touch up on continuity later on. That just means that the function is defined everywhere, really. That's kind of what I want you to understand in this video. Continuity is just the function. I can plug in any value of the function, and it's defined everywhere. Sometimes you might see like does not exist. You might see that kind of writing. That just means that if I plug in if I'm evaluating a expression, it might it might not evaluate to some value. So if I divide by 0, for example, that does not exist because you can't divide by 0. So sometimes you can plug the limit value into the function, and if you get a specific value, that it'll work. So this next question says, what is the difference between the limit as x goes to a, where a is just some constant, of f of x, and the limit as x goes to a from the left side, and the limit as x goes to a from the right side of f of x? So again, I want to I want to draw a graph here to show you guys this. And, you know, maybe I can draw a parabola to maybe simplify things a bit. So this negative sign here indicates that we're coming from, I guess you could say, the negative direction. You're coming from the left side. So if I want to say, what is the limit as x goes to 0 from the left of f of x, I'm only going to consider this left side here. Don't consider this right side. If you're using the notation above right here, where it says the limit as x goes to 3, you're going to consider both the left side and the right side. But when you're using this specific notation of using a minus or plus above the number, you're going to consider only one side when evaluating the limit. So if f of x is just, well, this would be x squared, of course, because it's just this general parabola. You're getting really, really close to 0, 0, 0 from the left side. And then since this is a polynomial, all polynomials are continuous everywhere. So you can just directly plug in the value, and then you can say this limit equals 0. And then I'll just write f of x equals x squared for simplistic sakes. Now, what if I want to do the limit as x goes to 0 from the positive side of f of x? So just like before, but you're only going to consider the right side. So I'm coming from the right. I'm going towards 0, towards 0, towards 0. And now I'm really close to, limits you're not equaling the thing, but when you're evaluating them, sometimes you can just do the direct substitution method. So you're at this value right here, and this would be 0 again, because when you're approaching 0 from the right, you are really, really, really close to 0. Okay, now to end the video, an important, distinction I want to make is the limit as x goes to a, where and a is just some constant, of f of x does not always equal f of a. So we talked about that direct substitution method, where maybe we can just plug in the a value right here, but you can't always do that. And in pre-calculus, maybe there were some graphs you looked at when you were looking at what's called holes of graphs. So I would hope you could find the holes of graphs. So we're going to use that to analyze what the limit of this function is right here, and the value of what that is too, at x equals 3. So I'm going to rewrite this function. I'm going to say this equals, you remember your difference of two squares from algebra. I'm going to take the square root of the first term, and then the square root of the second term, and then I'm going to have, in between those terms, I'm going to have a plus, and then I'm going to have a minus. And then this is still divided by x minus 3. So since we have the same term on the top here and the bottom here, I can just cancel those terms. And then f of x equals x plus 3. Maybe that's something you did in pre-calc. Hopefully it is. But that's just how you would simplify a function right there. And then an important note I want to make is if I were to draw a graph of f of x at x equals 3, for example, or around that area. If I just graph y equals x plus 3, that's just a line, right? So I'm going to draw that's at 3. That's a y-intercept of 3 right there. So I'm just going to draw my line right there. Arrows. So the thing with this function is if I plug in x equals 3 to the original function, what you're going to get is 3 squared minus 9 is 0, and then 3 minus 3 at the bottom here is also 0. So you have 0 over 0. Now, what we said before was if you divide by 0, that is we call that an indeterminate form. That's not a value that exists. So in pre-calc, hopefully you were looking at the example of holes. So if I go up here, there's going to be a hole right there. And, maybe I can draw this better, but I'm just going to get rid of that there. Draw my line in again. And then let's say x equals 3 is right there. So I'll write this again. So at x equals 3, there should be a hole right here. You're going to physically draw a hole. Like if the question asks you to graph f of x, you're going to draw a hole right there because that value doesn't exist at x equals 3. So the next question says find f of 3. Well, f of 3, we said there's a hole right there because if I plug in, you always want to consider the original function. It doesn't matter if you simplified it or rewrote it. You always want to, if you're evaluating the function at some point, you need to plug it into the original expression. So f of 3 equals, and we don't want to, I shouldn't say equals because you can't equal something that doesn't exist. So f of 3, we're going to say dne, and that's just, before I said that's notation for does not exist. And you're not going to write equals does not exist because that's not proper notation. You can't equal something that doesn't exist in math. And then the next question says, what is the limit as x goes to 3 of f of x? Well, if we look back at our graph here, if I get really, really, really close from both sides, I'm actually going to approach 6. And when evaluating limits, you always want to try to maybe look at the simplified version. But again, you can always try direct substitution immediately. That's what you should be doing right away. Because you want to solve the problem the quickest. But we got 0 over 0 here if we try direct substitution. So we need to try this simplified expression right here. So, this equals, this equals 3 plus 3, because I'm looking at this new simplified expression, and then that equals 6. Okay, and that should wrap up this lesson. If you have any questions, leave them in the comments, and I'll be more than happy to address them. Thank you.